Good morning. Today I want to continue our discussion of gas laws. In the last class we looked at Boyle's law, which gave us the inverse relationship between pressure and volume. And we looked at Charles' law, which gave us the direct relationship between volume and temperature. So we have one more sort of basic gas law that we can explore, and that is what's known as Avogadro's law. So Avogadro's law looks at the connection between volume and moles, right? So we've seen volume and pressure, we've seen volume and temperature. Now we're going to look at volumes and moles of gas, or the amount of gas. So the essential question is, what happens if we add more gas, right? Well, if we look at a graph, simple graph here, right? If we keep adding moles of gas, we see a nice linear increase in the volume, right? This is not a huge surprise to us, right? This is probably the most straightforward law to understand because we've all experienced this, right? Just blowing up a balloon, right? The simplest example we can have, right? If we put more gas in, the volume gets bigger, right? So the basic idea of Avogadro's law is if you add more moles of gas at a constant temperature and pressure, right? So as with the other laws, we always keep the other two constant, then the volume will go up. So we have a direct relationship between the moles of gas and the volume. Now again, just like the other two relationships, it is, as we saw in the graph, linear, right? So if I double the moles of gas, I get double the volume, etc. And as I said, we call this Avogadro's law because it was discovered by Amedeo Avogadro. If we were to write this out as a proportionality like we have the others, we would show that direct relationship. So as volume goes up, it's proportional to the amount of moles. So there's a direct proportionality there. So again, the simplest demonstration that we can come up with is just simply blowing up something like a balloon. So if we know that we just keep adding more moles of gas, we increase the volume. So now that we have our three basic laws, right? We have Boyle's law, we have Charles' law, and we have Avogadro's law, and we can show them in terms of a proportional relationship, where Boyle's law has the inverse relationship with pressure, Charles' law shows the direct relationship with volume, with temperature, and Avogadro's law shows the direct relationship with the moles of gas. Now, if we take all of these proportionalities with volume and put them all together, we get a relationship that looks like this. So volume is proportional to the moles times temperature divided by pressure. Now, while this proportionality is useful, right, it doesn't really help us in actually solving problems. Right? We need an equality, right? We need to turn this proportionality sign into an equal sign. And typically the way we do that is there's some sort of proportionality constant, or typically we just see them as constants in the equation, values that we have in the equation that are there to give us an equality. We don't usually even think about them being there, they're just part of the equation. Now, for gas laws, right, that proportionality is called the gas law constant, or the gas constant, and we abbreviate it with the letter R. And so our new equation, right, if we add in that proportionality, is the volume is equal to this constant R times N times T divided by P. And this is what we will come to know as the ideal gas law. Now, you've probably seen this equation before if you've taken a chemistry class, but probably not in this form the way we typically write it is in this form, where we've moved pressure over to the left-hand side so that we have P times V, or pressure times volume, equals the moles times R times T, right? So this will be our ideal gas law. Now, the value of R, right? We need to have a value of R. And this is 0.0821. Now, the units here become really important, right? Because the units of R dictate the units that we have to use for the rest of the values in our equation, because our units have to eventually cancel. So if we look at this, to use the ideal gas law with this gas law constant, the pressure must be expressed in atmospheres, or ATM, right? The volume must be in units of liters. Of course, N represents our moles of gas, right? Our MOL there. And our temperature, as we've talked about before with these gas laws, is going to be expressed in Kelvin. So this is important, and this is a difference from the problem that we saw last time with the combined gas law, where we used different units, right? We used millimeters of mercury for pressure, or we used milliliters for volume, right? And it didn't matter there, because as long as we kept the units the same, they would cancel out in the end. But here, once we had introduced this constant, we are locked into specific units. So we've got to pay close attention to that when we're solving problems. So now that we've talked about the ideal gas law, let's do a problem involving the ideal gas law. So the problem we're given says to calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atmospheres and a temperature of 315 Kelvin. Now, one of the big things that we'll run into here when we solve these gas problems is deciding on what equation to use, right? And so we have our individual gas law equations, right? Boyle's law, Charles' law, that we could use, right? But we clearly can't use those here because we're given other numbers, right? We're not given two sets of numbers, right? That we can't. So if we want to use Boyle's law or Charles' law or even the combined gas law, the key is those are dynamic, they're changing, right? The ideal gas law is going to be used in more static type problems, right? Where we're given a set of data and asked to find a missing quantity. And that's clearly what we have here. Now, I'll talk about this a little bit more in a separate video where I do just a couple problems to sort of show the difference. But here we have a clear example of where we're going to use the ideal gas law. We're given the moles, we're given the pressure, we're given the temperature, and just simply asked to calculate the volume. So, if we write out our ideal gas law, right, we have PV equals nRT. And if we make a list of what our values that we know are, we know the pressure is equal to 1.37 atm. We know our volume is equal to 0.845 the volume is what we're trying to find in this particular problem, so our volume is unknown. Our moles are 0.845 moles, and our temperature is 315 Kelvin. And of course, R is our gas constant here, and that's 0.0821 liter, atmospheres, mole, Kelvin. So we have our units, and we're going to then, or we have our values. We're going to go ahead and plug them in. Now, we should always check here to make sure we're in the right units. So remember, we need our pressure to be in atmospheres, our volume to be in liters, our moles in moles, and our temperature in Kelvin. So we all are matched. So we can go ahead and plug them in. Now, I'm going to go ahead and rearrange the equation before I plug things in. Now, you can do it however makes sense for you. You can plug in the numbers and then rearrange, or you can rearrange with just the variables and then plug in the numbers. So I know I need to get volume by itself, so I'm going to divide both sides by P, and my P's will cancel on this side, and I'll end up with volume equals nRT over P. So if we go ahead and plug in our numbers, we have 0.845 moles. We have R. And we have 315 Kelvin, all divided by 1.37 ATM. If we do our math here, we do this, we get a volume that equals 16.0 liters. Right? And we can see here that our units cancel, right? If we check our units, right, our moles cancel here, our kelvins cancel here, and our atmospheres cancel here and here. And we're left with simply liters as the units for our final answer. So that's a simple example of an ideal gas law problem. And again, I'll post another video that has at least one more example of the ideal gas law and the combined gas law. Okay, so that's an ideal gas law problem. Now, the ideal gas law is very useful, right? We can essentially use it to find a missing variable when we know all of the other three values. But it can be used for some other applications. One that we'll explore a little bit here just by looking at an example problem is it can be used to help us determine the molar mass of a gas if we combine our gas law readings with a mass measurement. So if we're in lab and we can measure, say, the pressure, the volume, the temperature, but we can also measure the mass of the gas, we can use this as a way to help us find the moles of gas and ultimately the molar mass of the gas. So let's look here at our sample problem. So we're given a sample of gas that has a mass of 0.136 grams. It has a volume of 0.112 liters at a temperature of 298 Kelvin and a pressure of 1.06 atmospheres. And we're asked to find the molar mass. So if we list out our knowns, right, we know our constant. Our goal here, right, is first we have to find N, right? So we know everything except the mole. So the key, one of the key things that we have to remember here, right, is understanding that the molar mass, right, what we're trying to find here is the ratio between mass of a sample and moles of a sample, right? It's grams per mole. Right? Now, we most commonly think of this as the number we can find on the periodic table, but we can find the molar mass of any sample if we know the mass of a given quantity and also how many moles that given quantity represents. It's just simply the ratio of the mass of a sample over how many moles that sample represents. So we know the mass here, but we need to find the moles, right? So we have our mass, we're given that. So our goal here is to find these moles. And we have a nice way to do that. Of course, since we know the properties of the gas, right? We know its volume, temperature, and pressure. We can simply use the ideal gas law. So if we rearrange the ideal gas law to solve for N, right, we get PV over RT. We simply plug in our values of P and volume. We plug in our gas constant, our temperature. We cancel out our units, and we see that the only units that are left are moles. This is going to be the units of our answer. So we do our math, and we end up with 4.85 if we stop at 3 significant figures, times 10 to the minus third moles. We can then use this in our molar mass equation, and we can take the ratio of the mass of this sample, which is 0.136 grams, and how many moles of sample we have, how many moles of molecules we have here, right? 4.85 times 10 to the minus third moles, and we get a molar mass of 28.0 grams per mole. So this kind of problem doesn't tell us what the gas is directly, but it gives us a pretty good idea of what some of the probable gases might be, because now we know that it has a molar mass of 28 grams per mole. So that's going to bring our study of gas laws to a conclusion. I will post one other video right after this, which will give some sample problems, and then there is one other section that I'm going to add on to this, and that's going to be looking at reactions with gases. So we're going to revisit our stoichiometry, but instead of working with solutions or solids, we're going to be working with gases, and we'll look at how we can use the ideal gas law combined with stoichiometry.